In this video, we will define the basic circuit variables such as current, voltage, and power that are used in circuit analysis. We begin with the definition of current, which is defined as the rate of change of charge. If we denote current with the variable I of t, then this is equal to the differential of Q of t. The current I of t is flowing through an element. If we represent an element with a black box, which is connected between terminals A and B, then the current is flowing in from one terminal and is shown by an arrow, and flows out of the other terminal, again shown by an arrow. For ease of representation, we will simply draw one arrow next to the element and write down the current I of t next to the arrow. This direction of the current is called the reference direction, which is that we are making an assumption that the current is flowing from A to B. The actual value of I of t may be positive or negative, and if we have a graph for I of t, which may have a shape like this, between 0 and 1 second it is positive, and between 1 and 2 seconds it is negative. So what this means is that we can break up into two cases. Case 1, which is the time interval from 0 to 1 second, where I of t is positive or greater than 0. What this means is that positive charged particles are actually moving in the same direction as the arrow. Or equivalently, negative charged particles are moving opposite to the direction of arrow. In the second case, when the current is negative, which is during the time interval from 1 to 2 seconds, I of t is less than 0. What this means is that the positive charge particles are actually flowing from B to A, or equivalently, negative charged particles are flowing in the opposite direction. Thus, we can set up the direction of current to be in any direction and then interpret the value of the current that we obtain appropriately. The units of current are called amperes, and if written in full, we write it with a lowercase a, and when written as an abbreviation, we simply write it as a capital A. 1 ampere is equal to 1 coulomb per second. Next, we will define the variable voltage, which is also called the electric potential, or simply the potential. Voltage is defined as the differential of work with respect to charge. The voltage V of t is defined as the differential with respect to charge of the work done, where we are representing the work done as U of t. Voltage is a quantity that is measured across 2 points. Once again, if we draw an element as a box, which is connected between two terminals, A and B, then the voltage V of t is the value which is measured across the element, or from point A to point B. We usually give the voltage a reference direction by putting a plus sign on one side and a negative sign on the other side. This is the reference direction with respect to which we will measure the voltages. And if the voltage has a graph as a function of time, which changes as shown, such that between 0 and 1 second it is positive, and between 1 and 2 seconds it is negative. We can interpret this as two cases. Case 1, which is in the time interval from 0 to 1 second, where the voltage is positive or greater than 0. What this means is that the terminal A is at a higher potential or at a higher voltage as compared to terminal B. In the second case, which is during the time interval from 1 to 2 seconds, B of t is negative. What this means is that the terminal B is at a higher potential as compared to terminal A. Thus, it is important to set up a reference direction and interpret the value of the voltage appropriately. The units of voltage are called volts, and we write it with a lowercase v if we are writing it in full, or as a capital V if we are writing it as an abbreviation. 1 volt is equal to 1 joule per coulomb. Very often we will choose a point in the circuit to be the reference node or the ground node, and we will denote it by a symbol such as a triangle with a few lines, or a triangle pointing downwards, or the following symbol. The voltage at this node is always taken to be 0 volts, and all other points in the circuit are measured with respect to this ground node or reference node. For example, we can draw an element and connect one end of the element to ground. Let that be the node B, and the other node of the element is at node A. Then the voltage at node A will be measured with respect to B, with the understanding that the voltage at node B is 0. Power is defined as the rate of doing work. If we denote power with the variable P of t, then it is the differential of the work U of t with respect to time. We can rewrite this equation such that the energy is a function of charge, which is a function of time, and write the differential first with respect to charge and then multiply the differential of charge with respect to time. We recognize the first differential as the voltage V of t and the second differential as the current I of t. Therefore, power is the same as the product of voltage and current. The units of power, watts, and if we write it in full, we write it with a lowercase w, and if we write it as an abbreviation, we write it simply as a capital W. 1 watt is equal to 1 joule per second, and as shown above is also equal to volts multiplied by amperes, or 1 watt is equal to 1 volt ampere. Since power uses both voltage and current, to calculate power we need to know both the voltage and current for an element. As discussed previously, both voltage and current have reference directions, and therefore to calculate power we have to link the reference directions of the voltage and current. This linkage of voltage and current reference directions follows certain conventions. The first convention that we will talk about is called the passive sign convention. If we have an element connected between nodes A and B, and we denote the reference direction of the voltage V of t such that we take node A to be positive with respect to B, and we draw the direction of current going from the positive end of the voltage towards the negative end. Then it is called the passive sign convention. Note that the current I of t reference direction is always taken to be from the positive end of the voltage reference direction to the negative end. If we follow this convention, then the power absorbed by the element is equal to the voltage V of t multiplied by the current I of t. The power absorbed is often also called the power received or the power dissipated in the element. It is also called the negative of the power supplied by the element, or negative of the power produced by the element. If we do not follow the passive sign convention and draw the direction of current in a different way, such as where the reference direction of current I of t is going from negative end of the reference direction of voltage towards the positive end. In this case, the product of V and T will give us the power supplied by the element. It is important to be very careful, and in this course we will use the passive sign convention exclusively. We will solve a simple example of power calculation. Consider the element shown on the screen, which has 5 volts across it and 2 amperes flowing through it. We notice that the current and voltage follow the passive sign convention, and hence the power absorbed by the element will be the product of the voltage and current as shown, such that it will be absorbing 10 watts of power. We can show the same element and draw the current and voltage in a different direction. We will keep the voltage polarity to be the same, and it is 5 volts. Direction of current will be changed, and the current will now become minus 2 amperes. Since this voltage and current do not follow the passive sign convention, the power supplied will be equal to the product of the voltage and current. In this case, 5 volts multiplied by minus 2 amperes, which is equal to minus 10 watts. Notice that we have changed both the direction and value of the current, therefore it really represents the same element as in the previous case, and as a result the power absorbed by this element is also the same as the first case, which is plus 10 watts. Therefore, the second case did not follow the passive sign convention. However, we calculated the power carefully and found that the element is absorbing a positive 10 watts.